Have you ever stumbled upon this bizarre term called Mutex? Sure, you might know it has something to do with protecting data used by threads by locking and unlocking memory access or something like that, but beyond all that, do you actually know when to use it, how it works, and what its better alternatives are? I guarantee that if you haven't responded with yes to all of these questions by the end of this video, you will skyrocket your concurrent programming skills. But let's start with the fundamentals. What is concurrent programming? Let's understand what is concurrent coding by understanding what is not concurrent coding. Take a look at this program. It's written in C, but the actual language doesn't matter. The idea behind it does. This is an example of serial code. Its instructions are executed sequentially, one after another. Each operation must end before the next one begins. So function A happens before B, which happens before C, and so on. Everything in order. This makes perfect sense, and it's a piece of code that's actually easy to debug because its issues are pretty obvious to find. So if function B doesn't work, you might want to check function A or B itself without having anything to do with C. But this entire process is slow as hell for the CPU to calculate. Imagine your CPU has many cores, and what does a core do? It runs a serial program. Your CPU might have up to 24 cores, each capable of running a program. Using only serial code in your workflow means you're limiting yourself to only 1/24th of your CPU power. Or just 1/4 if you're using an Intel Core 2 Quad, which is probably older than me. But still, do you understand why sequential code isn't used when creating decent performance apps? You waste resources by not using some form of parallelism in your code. So, does concurrent programming mean using all your CPU cores to execute instructions? Yeah, but no. So the idea is that the thread, which is basically a series of instructions, runs on one core, where the instructions get executed sequentially, while other threads run on other cores, right? That's true sometimes. Your computer can open way more than 20 apps at a time, despite you only having 4 available cores. That's because a core can run more threads, but not at the same time. Here is the catch. It runs a bit of one thread, then a bit of another, and so on, until it gets back to the original thread and repeats the process. That is concurrency. It's not strictly parallelism, but it represents doing a bit of everything one by one. It's really important to understand this fact. A single core is capable of running multiple threads in an interleaved fashion, rapidly switching between them, creating the illusion that they are happening in parallel. A core executes a bit of thread A, then a bit of thread B, then so on until it gets back to thread A and executes the next bit. And this is why concurrent programming turns your perfectly synchronized logic into a massive clusterfuck. I mean, you don't even know when instruction happens. Is it before or after B? Like, what if the data produced by A is needed by C, but instruction B is happening in parallel and somehow messes with A's work, which in turn results in C not working? Heck, you won't even know if A will arrive at all. Okay man, concurrent programming is hard, and this is why I made this video. To equip you with the tools and the proper mindset to approach all of these difficulties. Today we're discussing log-based techniques and algorithms, which also includes a mutex mentioned in the beginning for clickbait. But this is not even half of the story of concurrent programming, so I'm going to ask you to do the usual YouTube algorithm stuff. Drop a like and a comment so this video can spread to more people who could benefit. Okay, I'm just kidding, drop a like to make me famous. Now, grab a popcorn, or some beef brain grass-fed desiccated both in brain capsules or whatever you're consuming, and let's dive into log-based programming. Given two threads running simultaneously, if they both need to modify a shared object, they will fail pretty badly. Let's say thread A increments some value and goes to do some work. Thread B multiplies that value and goes doing another work. The result is 22. But if B executes first, then A, the result is 21. If you've attended your primary school class, you might know that generally the order of operations matter. So it's here, the final result depends whether A executed before or after B in this case. The correct order is whatever you want, The important thing to grasp here is that threads don't have an imposed order. Your operations might execute at unexpected times. When that happens, you probably get corrupted data, and many times you encounter hazen bugs because of this, which are those bugs that randomly disappear when you enter the bug release or magically pop out and come back sometimes. You know what I'm talking about, right? The situation we've been earlier on, where A and B both chase a value, is called a critical race condition. Whoever gets to X first determines the output of your program. If we view the operations in their decomposed form, they can also interrupt each other in nasty ways. Like if B reads the data first, then A reads it before B has a chance to modify it, you'll get a data race situation. A's work is overshadowed basically. Any situation on which the behavior of the program depends on timing is called a race condition. A race condition that can cause bugs or any unexpected behavior is called a critical race condition. Now, why the heck have I made this entire fuss about corrupted data, data races and race conditions, instead of summarizing it all in one phrase? Because the main point of this video is to eliminate data races and race conditions. And a solid understanding of what the problem is, it's always a good first step in solving it. But hang in there just a bit more, we've got some more theory to discuss before getting into something practical. An atomic operation is a task that cannot be interfered with. For example, if thread A performs an action on object X, it's guaranteed that no other thread can negatively impact thread A's data, even if thread A's execution is paused. Got it? Atomicity equals freedom from interference. This concept is crucial to understand as we'll use it many times in this video. Here is a fancy definition. An atomic operation is an indivisible action that guarantees data integrity and prevents interference in multi-threaded or concurrent systems. Again, in simpler terms, it will execute safely as long as the thread runs. Logically, such operations are free from data race bugs since they are safe from harmful interruptions. We can classify atomic tasks into two categories: natural and artificial. Some primitive tasks like reading a 32-bit integer on the average CPU is naturally atomic. These operations are so lightning fast that they cannot be interrupted until they complete. However, in your code you'll encounter more complex instructions like incrementing a value. As we discussed earlier, if two threads try to increment the same number simultaneously, data races can occur. For these cases, you need to implement atomicity manually, hence why I call them artificial. Take a look at this example. If we consider this function to represent an operation, it can be split into two events. The invocation event, which represents the start of the operation, and the response, which represents the end. We'll say from now on that an operation is executed atomically if nothing interferes with the data between the invocation and response events. Understand that it's perfectly fine for an operation to be interrupted by non-critical tasks. Our job is to prevent external operations from manipulating the critical data between the invocation and response events. That's why I only highlighted the middle section. It uses GQueue, which is a global shared value. The other sections can be interrupted safely. Now, how the heck do you stop other threads from messing with your thread's data? There are many ways, some better than others, but you must be aware that your OS provides some excellent tools for writing concurrent code. They are called synchronization primitives. Those tools allow you to fix every single problem we've discussed about earlier with ease. They allow you to make whatever section you want atomic so nothing will interfere with it. We'll also discuss synchronizing threads. When one sleeps, which means it's not ready to run on the CPU, other one runs. With all of that said, what is a mutex? A mutex job is to make any section of code atomic. It's fairly easy to understand, like take a look at its general API. It consists of create and delete functions, delock and unlock methods, and finally the try lock and try unlock. How do you use a mutex in your code? So first step, you identify a critical section. Yeah, that section you think is dangerous. That's the danger zone. You'll set up a mutex using the constructor, then wrap the dangerous fragment with .lock and .unlock. Wrap every danger zone related to this chunk of data from other threads. Make sure to use the same mutex object. Don't create mutexes for every thread unless you want to lock different chunks of memory. And you're done. But still, how does it work? Well, the mutex will be locked after the deadlock is called, and unlocked after the .unlock is called. Pretty logical, right? Thus, if the thread N tries to execute a deadlock and the mutex is already locked, that means the data is already used by another thread and N goes to sleep. It wakes up once the other thread unlocks the mutex. The methods try-lock and try-unlock work exactly the same, but won't put to sleep the current thread if it fails to lock. They return a success boolean. Let's see how it works in good old C. The following example consists of two threads, A and B, both working with a shared counter. To prevent data races which appear when A interrupts B in mid-execution or vice versa, we use mutexes. The final value printed should be 2. Thread B will wait for A to finish using the counter, then it will resume. And of course, it can also go the other way around, A can wait for B to finish. It's also good to know that using try-lock is frequently used as well, since you can prevent the thread from going to sleep and make it do some useful work while waiting for the unlock event. The critical section. It is a tool provided by Microsoft which works exactly like a mutex, but the mutex is more expensive to use since it requires a kernel call. The API is sort of similar. First, initialize your critical section object, then you use enter critical section before your code's critical section and exit critical section afterwards. If you also have manners, delete it after using, and you're done. The way it works is pretty straightforward. The threads are put in what's called a spinning state, that is initially a while loop that repeatedly checks if a condition is met, something we call busy waiting. It sounds inefficient, but it's smarter than it seems. Modern implementation optimizes this by pausing a thread if it's spinning for too long, so it doesn't use resources unnecessarily. On top of that, they might also add slight delays before rejecting the condition, spacing out the checks to reduce the overhead. Note that the critical section also might make a kernel call if it waits for too long, but essentially that's why it's much faster than the mutex. It only calls the kernel when it needs. However, keep in mind that the critical section, unlike mutexes, can be shared across multiple processes, so think twice about using them if you wish to share them across multiple programs. What if a mutex could support multiple readers and writers of some shared data? That's what a semaphore is, another tool similar to mutex, but it allows up to n threads to access the data. When it comes to the API, it has initialize and uninitialize methods, the .take and .give, which are akin to the mutex lock and unlock. A semaphore includes an inner counter. On .take, the counter decrements, and on .give, it increments. So, for a thread to access the shared data, it calls .take. Internally, the semaphore verifies if the counter is greater than 0. If it is, the thread accesses the data. Otherwise, it will be put to sleep until another thread exits the semaphore. It's important to note that a semaphore could be released by any threads, unlike the mutex that can be locked by thread A and only be unlocked by thread A. It's mainly used to restricting threads to a fixed number of resources. For example, if you are rendering graphics and you need to limit to n buffers, the semaphores will be pretty useful. Windows provides a synchronization primitive entitled event object. This is one of the easiest to use. Its API consists of wait for single object and set event. I believe you know how events work in programming. You have certain sections in your code that should run only when certain events occur, like an ambulance in traffic. Once the cars in the traffic are notified by a siren noise, they let the ambulance take priority, so they move aside or whatever they do. In essence, an event object is a notification mechanism. They are used in thread communication for obvious reasons. In this case, a thread can wait for an event using the wait for single object, and another thread signals that event by using set event. The promise and future are some related synchronization primitives. Pay attention to this, since it's used quite often in domains like game development and web development, I guess. You use promises to receive data produced by worker threads. Any thread that's main purpose is to generate data is called a worker thread. Promises are used to safely access data from their thread once it's done. Take a look at this example. you spawn a thread A inside the main function, and it's supposed to calculate every prime number between this range. The task itself doesn't matter, the idea that I want to access its output is the important concept. The promise is a holder of data. The future is an obtainer of data. As an analogy, think of the thread using the future as a consumer and the thread creating data as a producer. In this case, the producer promises the consumer that someday the data will be produced. In other words, the promise will be fulfilled. Thus to represents the concept of a contract, right? The future object is obtained relative to the promise object. Once the producer calls the thread the get, if the promise wasn't fulfilled yet, it will wait until so by putting the thread to sleep. And yeah, of course, that get returns the value. It's important to know how to use these stores, or at least be aware of how they work. Since you've got this far in the video, I believe you'll actually use them someday, so in the last bit of this video we're going to discuss about common issues that occur when using lock-based concurrency. Deadlock is a situation in which no thread in the system can make progress, resulting in a hang. Because no threads are runnable, no resources can become available and the entire program hangs. For a deadlock to occur, we need at least 2 threads and 2 resources. Take this example. Thread 1 holds resource A and is waiting for resource B, while thread 2 holds resource B and is waiting for resource A. Do you know in movies those scenes where 2 characters hold each other at gunpoint? Both are locked in plane waiting for each other to back down. That's similar to a deadlock situation. Of course, deadlocks can be more complex, involving more threads and resources, but the key factor that causes them are circular dependencies between threads and resources. Take a look at this graph. The squares represent threads, the circle represents resources, or more precisely the mutex that holds them. Solid arrows connect resources to threads that currently hold locks to them. Dashed arrows connect threads to the resources they are waiting for. If we eliminate the resources from the graph for simplicity, and we remain only with the dashed lines which represent thread dependencies, if such a graph contains a cycle, we have a deadlock. Actually, only the cycle isn't quite enough to appear. There are 4 questions you can ask yourself to determine if you have a deadlock. Those are the Kaufman conditions. First, do you use a mutex? Does any thread go to sleep while holding a lock? Is anyone able to forcibly break the lock of a sleeping thread? And lastly, does a cycle appear in your dependency graph? Avoiding deadlocks boils down to responding no to as many of these questions, since 1 and 3 are somewhat of a forced yes depending on your implementation. Solutions focus on solving 2 and 4. As a rule of thumb, of course, reducing the number of locks will make deadlocks less common. Try to find places where using 2 mutexes isn't necessary. Starvation. This is a phenomenon in which 1 or more threads fail to receive any execution time on the CPU. It can happen when 1 thread basically isn't allowed to run, even though it is runnable. For example, when high priority threads keep being executed by the scheduler and lower priority ones are omitted. If you didn't already know, a thread can be categorized as low or high priority, which is a property set by the programmer. Well, depending on your environment, the number of priorities will differ. On Windows there are 32 thread priorities, but same rules apply. After your core completes a section of your threads, it switches to another one. It generally prefers high priority threads even if they were already executed. The schedule hardware is responsible for selecting which threads to be executed. To solve priority-based starvation, make sure you don't set priority to threads without having this in mind. Always keep the high priority threads somewhat fast to compute, and if needed, algorithms like priority aging or phase scheduling might prevent all of this. Global ordering. So picture this. You currently code in a concurrent environment and you access a global shared double linked list, like ABC. This data structure is designed to provide fast new insertion and deletion of elements at any location. Like if you execute those 2 instructions, insert D before C and insert E before C, the resulting order of elements will depend on which of the instructions will execute first. If D gets inserted before C first, then E gets inserted before C, in opposed to the case where E gets inserted then D, If those two instructions come from separate threads, it can lead to inversion of elements or even corrupted data in some cases. It's a good rule of thumb to avoid this situation, but if you just can't, make sure to impose an ordering rule using the synchronization primitives discussed earlier. It's a very context dependent issue, so I will have to remain quite vague with it. So, in concurrent programming, it is generally implied to use global ordering across all threads. Okay, and finally this video is done, and let me tell you that I'm sick of working on this project. It's been so many hours of testing and reanimating and pre-recording everything I did. The thing is that I would like to leave you with some credits. So the first thing is that we have this book, which this entire video is a ripoff on a chapter from this book, and if you saw my camera shake, no, that's not an effect, that's actually the book, because it's heavy as fuck. It has probably a couple kilos. For Americans it's like, I don't know, 5 cheeseburgers or something, but it's fantastic. If you want to learn more low-level programming and level up your skill, it's great, and it's called Game Engine Architecture 3rd edition, so you will also learn to make a game engine. I haven't read it, but from what I've seen, it presents the core fundamentals, so you can apply them. It's not just I write, you write too, you copy my code. It's more like I teach you, you write your own code. I would like to mention also the CPU model you saw in the beginning of the video, the one where I was talking about multiple cores. It's stolen from Sketchfab, and if I don't forget to put a link in the description, you can search for it as imaginary CPU model or something, you'll find it. Did I say model or mother? So if you're an expert in this topic and you actually know something, unlike me, please correct me or correct anything in the comments. Yeah, I guess that's it. Hope you have a great time programming those concepts or whatever you will do. A great day, and see you in the next video.